Once again, slower. Watch the shadows of the eddies following the starboard quarter of the ship. We can visualize how it acts unevenly along the hull, having more effect aft than forward, and thus creating the turning couple. This phenomenon can also happen when moving astern. It is more likely to happen with the tug at the accommodations facing than at the forecastle break, since the force is acting closer to the center of lateral resistance. The azipod propeller of the ship was adjusted to produce nearly zero transverse thrust. For this phenomenon to happen, the following conditions must be present. The tug must be powerful enough and its action must last long enough to create sufficient side movement. A sufficient speed through the water is also necessary in order to get a significant part of the hull out of the ship-generated sideways current in a relatively short period of time. The poor turning effect of the bow thruster when moving ahead and its good steering properties when moving astern are well-known facts. A very interesting article on the efficiency of the bow thruster was published in a Nautical Institute book entitled Pilotage. In this article, Captain H. Henson explains that when the ship starts moving ahead, the high-speed stream of water expelled from the thruster bends along the hull. Its high-velocity flow creates a low-pressure area that pulls the bow in a direction opposite to the side we want to thrust it. The result is that the two forces tend to annihilate each other and the net thrust force is very weak. The bow thruster is simply losing its efficiency as the ship moves forward. The loss of turning effect has therefore little to do with the change of arm lever distance between the thruster and the center of lateral resistance. When the vessel is moving astern, the vacuum effect created by the thruster is much less significant since the hull area over which it acts is quite smaller. A light ship is usually trimmed by the stern. Its center of lateral resistance is relatively more aft than a loaded ship. This results in a shorter arm lever from the rudder to the center of lateral resistance. At first glance, this should lead to less steering efficiency. This short arm lever is overcome by the small inertia of rotation of the light ship, less mass to control, therefore quicker reaction, for approximately the same steering power. On loaded ships, the larger inertia of rotation, even if the rudder center of lateral resistance arm lever is longer, makes the ship slower to react. The following phenomenon can also complicate steering control, especially when some vessels are even keel or trimmed by the head. Let's take the example of a vessel moving north and initiating a turn to starboard. Once the turn is started, the center of gravity of the vessel has now a new direction, a bit to the left of the initial course. Because of inertia, the center of gravity wants to keep going that way. Meanwhile, the vessel itself has a different orientation. Let's say 030. The more important underwater area ahead, combined with overpressure around the bow of these ships, bring the center of lateral resistance well forward of amidship. This means that relative to the new direction of the center of gravity, the center of lateral resistance would be some distance d off to the right. That distance corresponds to an arm lever that can be high enough sometimes to accelerate the rate of turn even with the wheel in midship position. Steering such a ship is like trying to keep the arrow of a wind indicator tail in the wind. On the contrary, when the center of gravity of the ship is forward of its center of lateral resistance, it improves its directional stability. Azipod-driven vessels going astern and turning will best demonstrate the present theory. Their high side thrusting capacity will show a pivot point forward of amidship, even if the vessel is going astern, especially at low harbor speeds. In fact, I foresee the greatest usefulness of the present theory for those who handle Azipod and Z-drive ships. The lateral movement of the vessel is only affected by the lateral components of the forces acting on the ship. The center of leverage for lateral forces acting on the ship is the center of lateral resistance. The center of lateral resistance, initially between the center of gravity and the center of underwater surface area, shifts towards aft with a trim by the stern, and towards forward with a trim by the head. The center of lateral resistance shifts progressively forward as forward motion through the water increases, progressively aft as aft motion through the water increases. Once the position of the center of lateral resistance is estimated, estimate the relative position and effectiveness of the lateral forces involved. Consider the arm lever length and estimate the amount of rotation and the amount of side movement the force will induce. You can then estimate where the apparent pivot point will lie. The apparent pivot point is a consequence of these two movements combined. It is not a cause. It has nothing to do with the turning arm levers acting on the ship. A ship with high lift will develop less sideways movement. Once a ship has developed a swing and no more force is acting on it, especially at low port operation speed, the rotation effect and the ship-generated sideways current are the main factors determining the position of the apparent pivot point, which is towards the end of the ship going in the direction of the turn.